You've seen it, I've seen it. There's this constant blizzard of new AI architectures. Some of them, boom, they become the industry standard almost overnight. And others, well, they have these brilliant papers, but they just fizzle out. So what's really going on here? What's the powerful, unseen force that's deciding who wins and who loses? Well, I'll tell you, it's probably not what you think.
It's a question that honestly keeps a lot of researchers up at night. I mean, you come up with a model that's more expressive, it's more elegant, maybe it's even more accurate on paper. So why doesn't it actually get deployed at scale? Why do we keep coming back to the same fundamental building blocks over and over again?
The answer, it turns out, is surprisingly practical. See, in the world of massive-scale AI, the best idea, it doesn't always win. The most compatible idea wins. Compatible with what, you ask? Well, that's the million-dollar question, and it's the key to this whole thing.
It all comes down to this one concept, the hardware compatibility filter. Think of it like a bouncer at an exclusive club. An AI architecture only gets past the velvet rope and into production if its core operations play nice with how GPUs are physically built. And what do GPUs care about? Two things, really. Dense matrix math and respecting the memory hierarchy. You know, that constant, critical shuffle of data between the super-fast on-chip memory, the SRAM, and the bigger but slower HBM.
So here's how that filter works in the real world. A new paper drops and everyone gets super excited about the benchmarks. But then it hits the GPU primitives test. Can its core math be boiled down to those dense parallel operations that GPUs just love to eat up? If the answer is yes, awesome. It passes through the filter, it gets adopted. But if the answer is no, it almost always gets stuck in the lab as a cool research idea that never quite made it.
All right, so let's make this real. Let's look at this filter in action. We're going to dive into some of the concrete winners and losers from the last couple of years. And it's a pretty fascinating story of how gritty engineering reality so often beats pure theoretical elegance.
Flash attention is probably the most perfect example of this. For years, the big problem with attention wasn't the math itself, it was that memory bottleneck you see on the left. The old, naive way was constantly shuffling these gigantic matrices back and forth, and it was just choking the GPU. Flash attention won because it brilliantly reorganized the computation. It used a technique called tiling, basically breaking the problem into smaller bite-sized chunks that could all be handled right there in the super-fast SRAM. It didn't change the math, it just solved the memory problem. Genius.
And then you've got the flip side. Remember all the hype around cans a little while back? The theory was absolutely beautiful, but their core operation, this thing called spline evaluation, is a total nightmare for GPUs. It's irregular, it's messy, and you just can't parallelize it like the clean, dense matrix math that transformers are built on. You could say transformers speak the native language of GPUs, while cans are kind of stuck using a really, really bad translator.
Now here's another clear winner, and it's a beautiful one. Grouped Query Attention, or GQA. This idea is so elegant because it's so simple. All it does is share a few key and value heads among a bunch of query heads. And the result? A massive reduction in the size of that super important KV cache. Best of all, it didn't need new hardware, it didn't need custom code, it was just a change in the model's weights. It just sailed right through the hardware filter, no problem.
But you might be asking, what about state space models like MABA? They promise to kill the whole quadratic scaling problem of attention. And they do work, but only up to a point. Just look at this table. Up to the 7 billion parameter scale, yeah, they're proven and they're efficient. But the moment you try to go bigger, to 13B or 70B, poof. The evidence for them being used in production just vanishes. And why is that? Well, because their design fundamentally pushes against the GPU's greatest strength, which is massive parallelism. They hit a very real physical ceiling.
And then, of course, you have the ultimate hack that just sidesteps the filter completely. RAG, or Retrieval Augmented Generation. This is where you just connect your AI to an external database. Instead of trying to cram every piece of knowledge into the model's own memory, you just let it look things up. It completely offloads the memory problem. It requires zero changes to the core architecture. It basically treats the GPU like a reasoning engine, not a glorified hard drive.
Okay, so let's see how this filter and all these pressures led to what is arguably the biggest architectural trend happening today, Mixture of Experts, or MOE. And this isn't just slapping a new layer on top, it's a whole new way of thinking about computation itself.
The absolute key innovation here is this idea of conditional execution. So instead of every single part of the model firing up for every single token you process, the model learns how to route different tokens to specialized expert networks. It's actually learning where to spend its computational budget. That's a revolutionary idea. Now, you hear a lot of hype around MAUI. You hear these crazy numbers, like 5x or 7x speedups. But let's get real for a second. In actual production deployments, the realistic inference speedup you're going to see from an MOE model compared to a dense model of similar quality is about 2 to 3 times, which is still totally transformative, but it's grounded in reality.
And it is absolutely gone mainstream. I mean, Mixtral proved it could work in the open weights community. Grok proved it works at a truly massive scale. But the biggest signal of all, that came from Meta. After pushing their dense models to the absolute limit with Llama 3, they pivoted completely to Mo for Llama 4. When a leader that has invested so heavily in one approach suddenly changes their entire strategy, you know the game has fundamentally changed.
But there's a catch. We call it the context length trap. See, Mo's advantage is at its highest when you're working with short context lengths. As that context gets longer and longer, that nice 2 to 3x speedup starts to shrink. You get up to 32,000 tokens or more, and your advantage can drop below 1.5x. Why? Because the system gets bogged down by memory bandwidth again. Just moving all that context data and all those expert weights around starts to become the dominant cost.
So if these ideas are so great, why does it feel like they take forever to show up everywhere? Well, this brings us to a really predictable pattern in AI development, what we can call the infrastructure lag.
This is one of the most useful rules of thumb you can use for predicting what's actually going to get adopted. A simple weight-only change like GQA, that takes about 12 months. Something that needs a new custom kernel, like flash attention, you're looking at about 24 months for that to get properly integrated into standard frameworks. And a huge systems-level change like Mo, that takes a full 36 months, 3 years, to really percolate through the entire serving infrastructure. The cost of integration directly predicts the speed of adoption. It's as simple as that.
So where does all this leave us? If the core architecture is starting to stabilize because of these very real hardware constraints, where are the next big breakthroughs going to come from? Well, the answer seems to be a major shift in focus.
I think this quote just captures the moment we're in perfectly. For nearly a decade, we have been obsessed with perfecting the architectural container, making it as efficient and hardware compatible as possible. But now, the real cutting-edge innovation is happening inside that container. It's all about the contents, the training data, the optimization algorithms, the learning techniques themselves.
And DeepSeek R1 is a perfect case study of this. It achieved just incredible reasoning performance, rivaling the absolute best models out there. But here's the thing. It didn't use some radical brand new architecture. Nope. It used the same Mo and efficient attention building blocks we've been talking about. The secret sauce, the magic, was in their advanced reinforcement learning at scale. They got a breakthrough by innovating on the training, not the container.
So, what's the takeaway toolkit here? First, from a predictive standpoint, when you see a new paper, just ask yourself, does this thing map cleanly to GPU primitives? If not, it's probably a research bet for now. Second, strategically, it's time to shift more focus and investment into training innovation, RL, data curation, all that good stuff. And finally, tactically, just use the proven winners that work right now, flash attention, GQA, and MOE for when you need to scale. That's the playbook for building things that work today.
And that really brings us to our final question. We've built this incredibly powerful and efficient container. So now, the real race is on to discover what happens when we start filling it with smarter, more sophisticated contents. What incredible new capabilities are going to emerge when our focus shifts entirely from what we compute to how we learn? That, I think, is the next great frontier.